Welcome back to part 4 of the gas law chapters. What we're going to get into today is being able to solve for gas and how much that gas is mass is, if you will, the molar mass of a gas. This formula is kind of derived from several things and several ways to get around it, so I kind of want to show you where it came from. And again, the molar mass is how much a gas weighs. There is one thing that I do want to point out, and that is the unit. For molar mass. Okay, remember molar mass is always going to be grams per mole. Okay, let's just keep that in mind. I do want to kind of throw that out there at you. Grams per mole should be the molar mass. So where does it come from? All right, now let's talk about this. I'm just going to kind of talk about the pictures and we'll go from there. 32 grams of O2 is 1 mole. Now, where do we get that from? Remember, any 1 mole contains the mass of the compound, and 32 came from the periodic table. 2 grams of H2 is 1 mole, and then 17, technically 17.03, if you want to get more technical about it, grams of ammonia is 1 mole. But notice the interesting part, and this is kind of connecting all the topics we've covered previously. The fact that 32 grams of oxygen, 2 grams of hydrogen, and 17 grams of ammonia are all 1 mole, yet they take up the exact same amount of space. They all take up 22.4 liters. By this point, you should definitely know what that is. All right. So let's kind of go from there. Now we have this formula. We have this formula right here, which is D equals M over V. Well, what is that? What is that formula? That is your density formula. Remember, density is equal to mass divided by volume. All right, that's your formula for density. And then you have this other formula, which is density equals molar mass times the gas constant R times T. So these are two totally different ways to relate things. This is more or less of a solid, even though it can be for a gas. But what if you don't know the mass of the gas? Even though you know what the gas is. So if they give you two variables, they give you the pressure of the gas in the container, and then they also give you you can solve for the molar mass of the gas from the periodic table, and they also tell you the temperature at which the gas in the container is sealed at. You can convert and you can figure it out of what the density is, okay? So there are two ways they can approach this question. Number one, they can ask you, what is the density of this gas? Or number two, they can ask you, what is the molar mass of the gas? All right? And there's one other little point going to point out. Is for 1 mole of a gas, it's 22.4. Remember, because pressure will be at 1 atm, and then the temperature constant will be basically 273. And then that times the R value basically cancel it out, giving you 224 on bottom, okay? So that is where that came from. If it is 1 mole of gas, it would be the molar mass divided by 22.4, which is the volume of a gas at 1 mole, all right? So I just kind of wanted to point that out. Now, there is a formula that we can use, and it has a funny little acronym, and I'm sure you've already seen it, the molar mass kitty cat. I did not make this up. This is something that I've heard through trainings that I've gone through, and a lot of students love it. A lot of students can remember it this way. And what it is, the molar mass kitty cat, is all good cats put dirt, DRT, hang on, sorry, my apology, guys. Put dirt over their pee. And what does that mean? What does that stand for? Essentially, is the molar mass of a gas is the density times the R gas constant times the temperature, all divided by the pressure. All right, so that's kind of where we're going with this. Again, it's dirt, which is density, R constant, and temperature divided by P. So if you think it's funny and you want to be able to use it, it's a good way to remember it. I do not currently have the laws and the constants, the equation sheet in front of me. But I do think this formula is on it. I'm almost pretty sure that it is. There is one other note that I do need to make mention of, and down here at the bottom it says density of gases are grams per liter, not grams per milliliter. So please, if they do give you a a density of a gas and they give it to you in grams per milliliter, you're going to have to convert it. And let's talk about why you would have to convert it. Remember, what is R? And this is a good point to write this down. The R constant is 0.0821 liters times atmospheres over mole per Kelvin. So Latam over mole. So why can you not have it in milliliters? Well, it's an obvious answer now, is that your R constant has a liter value, okay? So that's number one. All right, so let's look at a problem. The density of a gas was measured at 1.5 atm. Well, notice the way this question is really worded kind of throws you off, because look at what it does. It says the density was measured at 1.5 atm. Well, notice what this is. Density and atms are not the same unit. Atm is a pressure, so the way they've got this question's worded, don't let it throw you off. In 27 degrees Celsius, well, that's an issue all within itself. We need to get rid of that. So let's change that to Kelvin, and that is going to be 300 Kelvin. And now it tells you, and found to be 1.95 grams per liter. So now you know that this is your density, okay? And then the question is, what is the molar mass of the gas? Well, this is when you have to use your formula. All good cats put dirt over their P. So dRT over P. And again, I do recommend you go ahead and do this at 1.95 grams per liter. I'm just going to write R because I don't have enough space and it's hard to write it on my iPad like that. But you need to go ahead and write in your R value, numerical, and your unit, Latam over mole. Your temperature is going to be 300 Kelvin, all over your pressure, which is 1.5 atms. All right, when you solve that, the answer that you should get, and I want you to punch it in your calculator, double check, make sure that you get it, actually comes out to be 32.0. And I'm going to stop right here. You've already seen me write it, so I'm just going to finish it. Remember I told you this a minute ago. The unit for molar mass is grams per mole. Now let's talk about where that came from, okay? Remember the R constants units, and I'm just going to write them right here. Liters times atmospheres over mole per Kelvin. Well, let's talk about how we know what it will be. Well, if you have the density, which is grams, well, there nowhere in this R constant does grams cancel. So that's one of the reasons. So grams must stay. All right, well, let's look. Liters is on bottom in your gram per liter, but it's on top in your R value. So your liters will cancel. Kelvin's on bottom, Kelvin's on top, so Kelvin will cancel. And then atmospheres is on top, and it's also on top and the bottom, so those will cancel. Which leaves you with grams left and moles left, which gives you gram per mole. So please, that's where that's going to come from if you're kind of confused on all that, okay? So hopefully that makes sense. Now, one other thing that I do want to point out is notice the numerical value that it actually turned out to be. 32 grams per mole. Does that number sound familiar to you in any way, shape, form, or fashion? And if it does, I'm proud that you actually correlated this. The molar mass of gas that's 32 is oxygen, O2. It actually has a molar mass of 32. So more than likely the gas they're probably trying to get you to understand is oxygen. All right, so just kind of throwing that in there to see if maybe you caught that. If not, try to connect those things. All right, here's just kind of an interesting way to look at something. What is the approximate molar mass of air? Interesting little question here, because a lot of you would read this word and not think anything about it. We know that air is a lot of different things. It's made up of nitrogen, it's made up of oxygen, it's made up of hydrogen, it's made up of carbon dioxide, it's made up of a bunch of different things. Now, again, it says approximate for a reason. So what we're going to do is, again, I'm just going to kind of make this short and simple and sweet. We're going to say nitrogen, just for the fun of it, is, let's go with about 80% of our air. And let's go with oxygen is about 20%. And I know what you're sitting here thinking. You're saying, wait a minute, that's 100%. You just told me there's H2 and CO2 also present in air. So how can you say that's 100%? Again, this is an approximate value. So whatever we approximate is probably going to be a little bit less than what we come up with, all right? So here's what we're going to do. We're going to take that 80%, and remember, 80%, and we're going to alter that, and we're just going to say 0.80, and we're going to multiply that times the molar mass of N2, which is 28. And again, this is grams per mole. And then we're going to add it to the 20%, which is 0.2. We're going to multiply that times the molar mass of oxygen, which is 32 grams per mole. We're going to multiply and add those up, and that gives you an approximation of about 29 grams per mole. And again, it's an approximation. It's probably a little less than that because we do have other things in the air, such as hydrogen, such as carbon dioxide, and other things. But it's just a good approximation. All right, now knowing an approximate molar mass, we can then find the density. What do we know about density? Remember, at STP, we have a density of, it was the molar mass divided by 22.4. We can go back and look at the previous slide if you didn't remember that. Or you could look at it from this way. You have 29 grams per mole, and then in 1 mole, now let me try this again. 29 grams per mole, and again, I want to make it logical. We want density, which is what? Grams per liter. Yes, density, grams per liter. So we need to get rid of moles. Well, if moles is on bottom, where do we need to put moles? If you said on top, very good. And then we do have a conversion because it says at STP. This is that end all know all important formula that in 1 mole you have 22.4 liters, which is exactly what we just said just a minute ago. And if you do divide these numbers, you're coming out with about 1.3 grams per milliliter. Okay, just kind of some interesting things. You all know about helium. When you inhale helium, it basically makes you sound like a chipmunk. It raises your voice. It changes how you sound. The reason why, you can get into the anatomy part of it, how it changes your vocal cords or whatever. But one thing about helium is that it is lighter than air. And again, air is consistent with things that are composed of everything in the atmosphere. But it talks about those 3 gases that float in air. So remember, when we talk about floating and sinking, we're not talking about heavier light. That's not what we're talking about, because bottles and things like that, big ships, they can be heavy, but necessarily they float. So how do you compare things that float versus sink? And it has everything to do with density. All right. Remember, what we said was the density of air is about 1.3. And again, it's probably a little less than this, but that's okay. So if the density is greater than 1.3, what will an object do? If you said it will greater than 1.3, it should sink. Well, what if it's less than 1.3? If you said float, fantastic. So let's talk about those gases. So some gases that are less dense than air that will float. One of them is methane, which is CH4. Another one is ammonia, which is NH3. And another one is carbon monoxide, CO, something that comes out of your exhaust engine, the exhaust from your engine of your car. All right, and let's talk about 3 gases that All right, my apology. I had a technical difficulty there. Let's talk about 3 gases that sink in air, which means they're more dense. All right, one of those gases that you can list would be carbon dioxide, CO2. Another one would be O2. And another one is, I'm going to write it up here, is C8H18. And if you know the common name of this, I'm going to be super impressed. This is octane. If you said octane, very, very, very good. And how would you know that? Well, remember the prefix for 8 is oc. And again, you probably don't understand the ane ending. If you ever have to take organic chemistry, you will understand that if you ever have an organic structure, that the ane ending means single bond. Okay, so all of the carbons have single bonds in them. All 8 of them are bonded together by a single bond. Okay, so that's where we're going with that. So moving on. at the very top of this, this is Dalton's law of partial pressures. And again, you should be able to see this at the top of your slide. Again, what it says is gas mixtures and partial pressures. All right, so let's talk about what it means by gas mixtures and partial pressures. Well, we know that it is very hard to get a gas that is pure. And what I mean by pure is it's the only molecule of that gas in the container. And if you look at these pictures over here on the right-hand side, if you look at this top picture, notice what we have. We just have these grayish-looking dots. There's 4 of them. This is considered a pure container of a gas. Why? Because it's the only thing in it. Now the one below it, that is also a pure container of a gas. Why? Because there's only red ones. But then, this is what normal containers look like. There are multiple things of gases in these containers. So let's talk about in terms of pressures and how that could be concerned. If you go all the way back to the very beginning, to the first lecture, we talked about what are gas pressures and how do they come about. Remember, the way we get pressures is by collisions, and the more collisions you have, the higher the pressure is going to be. You increase the temperature, you increase the velocity, you increase the energy, you have more violent collisions, so your pressure is going to increase. So in this top container, the only way we can have a pressure is based on what these 4 molecules do. All right? In the middle container, the only gas pressure that we're going to be able to have is from what these red molecules do. But here's the weird part. As soon as you start mixing gases, your pressures are going to be different, and here's why. Different molecules travel at different velocities. It's kind of something we talked about. If I were to get in a race with someone lighter than me, you would have the sense to know that someone lighter can travel at a faster velocity. But here is the key. Do not get this confused. Even though lighter particles travel at higher velocities, they contain the exact same amount of energy as a heavier particle. Because this is testing you, quizzing you. What is directly correlated or directly related to the amount of energy a molecule contains? If you said temperature, you're correct. The temperature is what gives it its kinetic energy. However, velocities are based on not only temperature, but also the mass of the molecule. So the lighter, the faster, the heavier, the slower. So they do have the ability to change the amount of pressure that they would induce, if you will. So the problem is that when we have a container with mixture of gases, the pressure is not just the sum of one of the gases, it's the sum of all of the gases. But the problem is each gas will produce its own value of pressure based on the size, the mass, and the velocity. All right, so in saying all of that, the pressure of a mixture of gases is the sum. Now, when it says sum, we know that that means to add. It's the sum of the pressures of the different components in the mixture. So essentially, P total, which means the total pressure, is the sum of the partial pressure of the first gas, the partial pressure of the second gas, plus, and Pn just means as many number of gas molecules that are in the container. If it's 3, if it's 12, if it's 80, you got to add all of them up. All right. John Dalton was the guy that came up with this theory and really put the practical mathematical approach to it. Okay, and I'm going to forewarn you, this next little topic, there are a lot of multiple choice points, and there's normally, and again I say normally, not every year, a free response question associated with this style of information and this topic of information. Okay, so John Dalton's law of partial pressures includes the concept of something called a mole fraction. One more time, a mole fraction. Now, just like we know molar mass is mm, molarity is a capital M, absorbance is A. Anything that has Kelvin temperature is K. The symbol for mole fraction is chi. Now, I know you're sitting there thinking, that is just an X. Why in the world do you have chi out beside that? Chi is a Greek letter. And if you really want to see how it's written, again, it's one of those funky things. If you ever see me handwrite it, I'm going to write it like that. It's just kind of a swoop, and then it has just a cross. Again, it is a Greek letter. It is chi, just like we have the summation sign. That is sigma, and all that means is the sum of. So essentially, I could have said the sigma of the pressures of the different gases. So again, it is the Greek letter chi, which basically looks like an X. And here's what I also want you to understand. If you'll kind of pay very close attention, I'm going to refer to something and then show you how it relates. What is the basic definition of a percentage? And hopefully you said it is part divided by whole. Well, a percentage is part divided by whole, but then what do you always have to do with percentages? Times 100. All right, well, here's the difference. I want you to look at this now. Chi A, which is the mole fraction of A, whatever gas A is the moles of A divided by mole of A plus mole of B plus mole of C, and then etc. Whatever else you have present if it's there. So notice what we just did there. A is the part we're searching for, and you are dividing it by everything that is present. Well, that's interesting. So basically what we're saying is we want the percentage. Almost. You want the mole fraction. And so what is the difference between mole fraction and percentage? Mole fractions are not times 100. So essentially it's the decimal version of your percentage. Super simple. Don't overcomplicate what it really is. All right? Do not overcomplicate it what it seems to be. It's just basically the percentage without multiplying it times 100. All right? So don't move your decimal when you're solving for mole fraction. So the moles of A divided by the total number of moles. And then from that, Dalton come up with this formula. What if I want to know the pressure of A? So basically what you're going to have to figure out is if this is gas molecule A, all right, if this is gas molecule, or the container for A, and this is the container for B, and I know the total pressure in this container. See, I know P total, and then I know how many moles of A I have, and I know how many moles of B I have, and all I know about the total container is P total. And the question then states, well, what is the pressure that gas A gives you? Well, you can use this formula right here. You can use the mole fraction of A times the total pressure, and that will give you the pressure of A. One more time. Let's talk this one more time. We know A has its own pressure. We know B has its own pressure. And when you put them together, you're going to get a P total. It means the total pressure. But the question is, they have given you this number. They've given you P total, and then they ask you what is the pressure of A. If you could just look at the pressure of compound A. Well, what they're going to have to do is they're going to have to give you, again, they're going to have to give you this, the moles of A. They're going to have to give you the moles of B. And you're going to have to calculate the chi A, or the mole fraction of A, and plug it into this formula, if you will. Okay. Now, the one thing I do want to point out is they may not be very explicit in how they give you your moles. It may be in grams, it may be in molarity, it may be in all kind of different things. But again, you're going to have to get the conclusional answer into moles. All right. So hopefully that makes sense. All right, the partial pressures of each gas and a mixture of a gas in a container depends upon the number of moles of that gas. The total pressure is the sum of the partial pressures and depends upon the total number of moles of gas particle presence, no matter what they are. So this is basically restating everything that we've done. So let's look at the first thing. The partial pressures are based on the number of moles. Again, so if we have two containers, that one container has A, one container has B, and then we put both of those containers together. Each container has its own partial pressure, and that pressure will come from the moles of that gas. All right. Well, then once we put those A and B together in the container C, the total pressure will have to come from each individual container. So A will have a pressure, B will have a pressure, and you add those together, which will give you the total pressure. Okay, so not only does the total pressure depend upon the partial pressures, but the partial pressures depends upon the total number of moles. Again, It's just kind of a recycling thing. So the way it works is the number of moles makes the partial pressure, and the partial pressure makes the total pressure. Okay, and so that's how you get that part of it. Okay, so hopefully that kind of makes sense. All right, so the mole fraction, again, even though the mole fraction is not explicitly in the curriculum framework, you should see that the ratio of pressures is equal to the ratio of moles in a mixture. Again, this is kind of overcomplicating the fact that what are we asking you for? We are asking you for the percentage of moles without multiplying it by 100. That's all we're asking you for. We're asking you for a mole of a certain compound, and what you do is you find the mole initially. Excuse me, let me go back. You want to find the number of moles. Again, why does this kind of look funny? Note N equals the number of moles. Okay, that's what it means. So essentially it's the moles of A, let's just call IA, doesn't matter, and it's going to be divided by the total moles. Okay. The only difference between the mole fraction, which is what we're looking for, remember it has the Greek letter chi, is just you don't divide by 100. So part divided by whole, if you want to write that above this, is part divided by whole. And again, it's all based on moles. Okay. So the mole fraction of nitrogen in the air is that. So we know, remember, mole fraction is chi. My apologies. Okay. We know that mole fraction is chi. Calculate the partial pressure of N2 in the air when the atmospheric pressure is 760 torr. Now, the only issue here is that we're going to have to do one small little conversion. To be able to do this seamlessly, give me just 1 second, please. All right, my apologies. I had to look something up real quick just to double check and make sure I didn't tell you incorrectly. All right, so let's get back to this. Remember, the mole fraction, again, is chi. So what we're trying to figure out is the partial pressure of N2 in the air when the atmospheric pressure is 760 torr. All right, if you'll go back 2 slides and look, remember, what we're looking for is the pressure of N2. And we had a formula earlier. Remember, it was the chi of N2, which was chi A, times P total. It's this simple. If they ever give you something this simple, please don't miss it. And again, I do believe that this is in your formula sheet. I could be wrong, and I would need to double check, but I'm pretty sure it is. And it's just a simple multiplication fact. So 0.7808 times 760 torr. That will give you an answer of 593 torr. 593 torr. So, again, how does this work? The total pressure, again, atmospheric pressure is 760. And of that 760, 593 of it comes from nitrogen. So then you could figure out the difference and know that the remaining pressure comes from other gases that are in the atmosphere. Okay, so hopefully that makes sense. All right. The partial pressure of oxygen was observed to be 156 torr. All right, so look what they just done. The partial pressure of oxygen, so PO, in the air with a total atmosphere of pressure of 743. So they then just gave you PT. All right, well let's think about this. The formula is going to be PO2 equals chi O2 times PT. And look what they ask for. They ask for the mole fraction of O2. Well, this is just a simple rearrangement of your formula. So chi O2 is equal to PO2 divided by PT. Very simple rearrangement of your algorithmic expression. So then you just plug your numbers in. So 156 torr divided by 743 torr will give me an answer of 0.210. And there are no units on this. Well, think about it. Duh, that makes sense. Torr divided by torr, torrs will cancel, leaving you with no units, okay? So let's talk about what does this mean. So what we're saying is the total pressure of the atmospheric pressure is 743 torr. Of that 743 torr, 156 of it comes from oxygen. And so what fraction of it would be from oxygen? Well, again, it's 0.2 is your answer. But if you really want to go and look at it even more, basically the percentage would be 21%, which we know is about true. Oxygen is about 21% of your atmospheric air. So this kind of double backs and should make sense to you, okay? All right, so that is the second problem. Let's look at one more problem. All right. Mixtures of helium and oxygen are used for scuba diving to help prevent the bends. Again, that's just getting nitrogen in your blood, which is not a good thing. For a particular dive, 46 liters of helium at 25 degrees Celsius. Let's get rid of that. We know we don't ever like temperatures like that. That's 298 K. And 1 atmosphere. Okay, so we have helium. And 12 liters of oxygen at 25, same thing, get rid of that, 298 K. And 1 ATM were pumped into a tank with a volume of 5 liters. All right. Calculate the partial pressure of each gas and the total pressure in the tank. All right, so we're going to need the partial pressure of each gas. One more time, we're going to need the partial pressure of each gas. All right, so here's the issue. Notice what they've done. They've given you a volume, a temperature, and a pressure for helium. They've given you a volume, a temperature, and a pressure for oxygen. And then it talks about calculate partial pressures and total pressures. Well, we know that somewhere along the line, we're going to have some moles in here. Well, again, that's going to be the aggravating part. We're going to need to be able to figure out how to get the number of moles of each one, okay? So again, this is probably going to be a long drawn-out problem, so conserve your space. It is going to take a few minutes to do this one, okay? So what we're going to do is we're going to solve for N of HE first. All right, so we're going to solve the number of moles of HE first. Well, again, they've given us the volume, the temperature, and the pressure. What do you think we're going to need? Hopefully you said PIBNERT. If you did, you'd be correct. So remember, so N, my apologies again. N is equal to PV over RT. So again, that's your formula. So your pressure is 1 atm. The volume is 46 liters. Again, sorry, I'm writing on an iPad with a stylus. I know it's kind of hard to see. And your R, again, I'm just going to write the letter R. You need to write out the numerical value and the units. Times your temperature, which is 298 K. All right, and that comes out to be 1.8 moles of HE. All right, now we're going to solve for N of O2. So again, let's see, we're going to have 1 atm. We're going to have 12 liters. And then we're also going to have, let's see, R, again, write out the numerical, write out your units, and it's going to be, again, also 298 Kelvin. So there's a large difference in your tank size, or volume size for these, okay? And your moles comes out to be 0.49 moles. And let's just go ahead and do this. You're also going to need NT, which is in total. So all we're going to do is just add this up, and that's going to give you 2.37 moles total. Okay, so that's what's going to give you there. All right, so we have our total moles. So let's think. We have our total moles. Do we have the ability to find our total pressure? Well, we should. Think about that. We know the total volume size. We know the total temperature. So we should be able to get our total pressure. All right, so this is kind of where we're going to take a little secondary tour here. So now we're going to solve for P total. All right, so PT is going to be, we're going to use PIVNERD again, which is nRT over V. All right, N. So what is N coming from? It's coming from our total number of moles. So it's 2.37 moles times R, and again, you need to write it out. And then I can't really fit it in, but I'm going to try 298 K because that's the temperature at which it says it is, 25 degrees C. Again, that's where we're going to plug it in. All divided by the volume, because notice what it says. We're pumped into a tank with a volume of 5 liters. All right, so it's going to be all over 5.0 liters. So that if you run your math there, you're going to get a total pressure of 11.6. Why not? Right? Yes, 11.6 ATMs. All right, so that's your total pressure of each gas. All right, so that is part one. But also notice what else it says. It says we want the partial pressure of each gas. All right, so keep all this in mind, and I'm fixing to clear this one more time. So now we want the pressure that came from helium once we mix the gases. Okay, we want the pressure from once we mix the gases up. Well, we know that our formula, and again, I'm just going to write it up here, the pressure of A is equal to chi A times PT. Well, we know our P total. All right, we know our P total is 11.6 ATMs. We just solved for that. All right, but what is chi? Remember what chi is. Chi is your percentage without multiplying times 100. So it's your moles of He divided by your total moles. Well, that's interesting. We've already solved for all of those things. So the number of moles of helium was 1.8. The total moles was 2.37. So if you will run your math here, you will find out that the partial pressure of helium in the gaseous mixture is 9.2 ATMs. All right, so now let's look over here at oxygen. So the partial pressure of O2, exact same concept. It's chi of O2 times the total pressure. So the total number of moles was 2.37, just like the other side, times 11.6. And the number of moles of O2 was 0.49. So if you run your math there, you're going to get about 2.4 ATMs. And here's where you can double check. This is what you need to be able to do. Does the pressure of the first gas plus the pressure of your second gas equal your total pressure? Well, 9.2 plus 2.4 equals 11.6. So yes, your partial pressures must add up to equal the total pressure. If that doesn't make sense, again, go back and rewatch it for the second time and see if something does kind of click, and go from there. On water displacement, I'm just going to kind of run through this relatively quick. I don't want to spend a whole lot of time on it because it is something that can get a little encumbersome, if you will. So we're just going to kind of run through this real quick. It's common to collect water by it's common to collect the gas by water displacement. And basically what that means is we're going to pump a gas into some water, and the gas is going to take up some room, and it's going to move the water. So let me finish reading, and I'll show you on the diagram. Which means some of the pressures due to partial pressures collected as the gas was passing through. You must correct for this, and this is what I want to show you. Imagine taking this solid. Let me go back. Imagine taking this solid right here, which is a potassium chlorate permanganate type of, or magnesium oxide solid. And what we're doing is we're heating this thing. Well, this solid is going to give off some gas. Okay, so what this is going to do, we're going to have the gas traveling up this tube, and notice it's corked. However, there is a piece of glassware that allows for some gas to escape. What's going to happen is the gas is going to take this pipe and it's going to travel down, it's going to go under the water, and then it's going to go into this jar and it's going to bubble. Now again, why is it bubbling? Well, a gas in a liquid is bubbles. And the two gases that were produced were oxygen and water vapor. Okay, water vapor. So when you have a gas inside of a container, that gas is going to start building up pressure. Well, the more and more we heat this solid, the more and more gas is going to go. Well, the more and more gas we get in here, the more and more pressure is going to build up. So the more it's going to force the water out of the container. And so what we can do is we can determine the distance right here, and that can help us determine how much pressure there was. Okay? So again, the total pressure minus the pressure of the gas equals the pressure of the gas collected. Okay, so an interesting concept. All right, so let's look at the next slide. So collecting gas and water. When a gas is collected over water, it is a mixture of gas and water vapor. So again, the total pressure is the pressure of the gas plus the water vapor. To find the pressure of the dry gas, you would have to subtract out the pressure from the water vapor. And again, if you go back and look, notice what happens. You have this oxygen gas travel through this water, and so it kind of maybe picked up a few oxygen gas molecules. Again, even if it's one, it can alter the total pressure because we're wanting the pure pressure of the gas that's being released. Okay, so here's the problem. The oxygen produced was collected by displacement of water at 22 degrees Celsius. Again, we don't like that. Let's go ahead and change that. So let's change it to 295. Okay, 295 Kelvin. At a total pressure of, all right, so they've given us something good. The total pressure was 754. The volume of the gas collected was 0.65 liters, and the vapor pressure of the water, notice what it just said, very, very, very important. The vapor pressure of the water at 22 degrees, 21 torr, calculate the partial pressures of O2. Okay, sorry, I kind of read this. The vapor pressure of water at 22 degrees Celsius, which is everything over here, is 21 torr. So notice what just happened here. I want to point this out. The total pressure was 754 torr, and the vapor pressure of the water was 21 torr. So that means that water vapor took up 21 of the 754 torr, 754 torr pressure. That was the total of it. And then it says calculate the partial pressure of O2 in the gas collected and the mass of the potassium chlorate used. All right, so we're going to do this one thing at a time. Well, first of all, we need to figure out the partial pressure of O2. Real simple of how we can figure out the partial pressure of O2. All right, so we know the P total was equal to the pressure of O2 minus the pressure of H2O. Real simple. All right. So the pressure of O2 was equal to, essentially, we're just excuse me, this is an addition sign. So we're going to subtract the pressure from the water from the total pressure, which is 754 torr minus 21 torr. All right. So the pressure from oxygen turned out to be 733 torr. All right. Again, that is the pressure of oxygen. Okay, the pressure of oxygen. All right, so that's taking care of the partial pressure, and then calculate the mass of the potassium chlorate. Now, here's the aggravating part. We know this, and they're asking us about the mass of this thing. This is why this gets a little bit aggravating. So what we're going to have to do is we're going to have to determine the number of moles of O2 and they go mole to KClO3, and then go mole to gram. All right, so let's just kind of follow along with me. But the issue here is nowhere, anywhere in this problem that they talk about the moles of O2. But what they do give you is the volume, and they give you a temperature, and you just solve for the pressure. All right, so pressure, volume, temperature. Hopefully in your head you said it. We need PIV NERV. So the number of moles of O2 is equal to PV over RT. All right, the pressure was what we just solved for, which is 733 torr. But there's an issue here. And this is something that I do not think the AP exam will do to you. 733 torr. Remember, we need to get that to atmospheres. So there is 760 torr in 1 ATM. All right, again, I don't have this worked out in my answer sheet, so I'm just going to kind of do it like this. 733 torr divided by 760. And we're just going to kind of leave it like this. We're going to use that as our P. You can solve it and write in the number if you need to. The volume is 0.650 liters all over R times T. And again, the temperature was 295. So I guess I could write that in. That'd be helpful for you guys. 295 Kelvin. And if you run your math here, you're going to get 0.0259 moles of O2. All right, so now what you're going to have to do is you're going to have to go mole to gram of KClO3. So 0.0295 mole of O2. All right, where does your mole to mole come from? It's 3 moles of O2 to 2 moles of KClO3. And again, that came from your coefficients. And then in 1 mole of KClO3, the molar mass of that is 122.55 grams. And so the final answer would be 2.12 grams of KClO3. And again, if you didn't get that one, go back and watch it one more time, and hopefully it will make sense to you to be able to do that. All right, I'm going to cut this video off. This is where we're going to end. The next time we pick up with a lesson, we're going to go over and review the kinetic molecular theory and finish up with the diffusion and effusion and a few things like that. Thank you for watching.